Welcome to Calculus. Today we will investigate finding derivatives of quotients and products. So we've looked at a product, now we'll look at a function that is a quotient, the division of two other functions, focusing on finding the slopes of tangent lines and particularly equations of any horizontal tangent lines to the graph. So let's take a look at our example. Our function here is f of x equals x squared divided by x minus 1. And notice we have a coordinate point given here. So the point is -1, -1/2. And I'm assuming that's a point that's actually on that function. And I can see that this is different from what we've just done with our product function, in that I start off finding the slope of the tangent line to the function at that point. So that's likely not going to be a horizontal tangent line. It'll have a non-zero slope. Well, let's begin by finding the derivative of that function. So since it is the division of one function over another, that clues me in that we're looking at an application of our quotient rule. So let's remember what that rule says. The quotient rule says if I've got a function big f of x, which I'm going to identify here as my little f of x. I'm actually going to overwrite, so this function is now big f of x. If that equals the division of two smaller functions, so the numerator small f of x divided by denominator small g of x, if I take the derivative of big f of x, it has this format. So it's small g of x times the derivative of small f of x minus the original small f of x times the derivative of small g of x. And then that's all divided by the original g of x squared. So there's our rule. Let's apply it. So I just want to identify which piece is which. So my x squared here, I'm going to assume is my small f of x. So we'll write that here. Small f of x is x squared. And the reason I need to take that aside is I need to find its derivative. So the derivative of that small f of x, derivative of x squared, apply our simple product power rule, is going to have the old power become a coefficient of 2, and then decrease the power by 1. So that's going to be 2x. And then similarly, I want to identify in my original, what's g of x? That's that x minus 1 denominator. And I'll write that here. Again, we want to take the derivative of that piece. So if that's x minus 1, the derivative of small g of x, using the rule that we have for the derivative of the linear x term is 1, derivative of minus 1, that constant 0, so that has the derivative of 1. So we're ready to fill in here. So let's populate our rule there for the quotient rule. So the original function g of x, I'm just substituting based on my labels, is x minus 1. The derivative of f of x is 2x. Original f of x is x squared. And then the derivative of g of x we found to be just 1. Now that's all over g of x squared, so x minus 1 squared. Let's reduce that down. So for my numerator, what I'm going to get there when I distribute 2x is 2x squared minus 2x. And then for my second product, negative x squared times 1 is just that, minus x squared. And then if I combine like terms, 2x squared in my numerator with minus 1x squared, that's going to be x squared minus 2x over x minus 1. And then just to help out with our next task, I'm going to factor that numerator to be x times x minus 2. So I see there's no cancellations, there's no removable discontinuities here. And that's my derivative of the original function. So if I look at my tasks here, part A is saying find the slope of the tangent line to the graph of each function f at the given point. So the given point is this -1, -1/2. So the part from that I need to pull is really the x value, because I want to substitute that into my derivative, and that'll tell me what's the slope of the tangent line at that point. So big F derivative at -1. And I'm just going to substitute into this rule that we wrote for the derivative. So -1 times -1 minus 2 over -1 minus 1 quantity squared. So that's going to be -1 times -1 minus 2 is -3. That's a +3 in the numerator. -1 minus 1 is -2. If I square -2, that's +4. So the slope of the tangent line is 3/4. And I can write that up here on part A. So that's good to find. I need to then jump to part B, because part B is saying find the equation of the tangent line to the graph of the function at that point. So I've kind of got part of that task done. What I need to do now is I need to fill in the point slope form to get the equation of the tangent line. So I'm going to label it, since we got a lot of calculations here with the derivative, equation of tangent line. And as I'm writing, try to decide how would you start setting that tangent line up. Which form are you going to choose? I'm going to choose the point slope form. Y minus y1 equals m times quantity x minus x1. And remember, there's three things to substitute for: the slope, x1, and y1. So I'm going to do that right here, right now. The slope we just found to be 3/4. And then x1, y1 are going to come from my point there, -1, -1/2. So I'm just going to clear out those variables, and let's plug in the numbers. So x1 was -1. So notice it's a double negative there, also on the other side, double negative. So that's going to reduce down. We want to take it from the point slope to the slope intercept so that we can graph well. So what I've got now is y plus 1/2, the double negative turns positive, equals 3/4 x. And then if I distribute to that +1, when those double negatives reconcile, that's +3/4. And then if I subtract half from both sides, that'll give me my slope intercept graphable form. So that's going to give me y equals 3/4x. 3/4 minus 1/2 is 1/4. And that finalizes part B. So part B was asking, what's the equation of the tangent line at that point? So that's y equals 3/4 x plus 1/4. Before we graph and kind of finalize this question, I have one more analysis piece where I need to find the points where the function has a horizontal tangent line. So recall, this is really where we started our task on the last question, where we're looking at the function that was a product of two functions. A horizontal tangent line means the slope is 0. And the way that I connect that with the derivative, remember, derivative is the slope of the tangent line. So if my slope is 0, to find that x value on the graph where that slope is 0, I would set the derivative equal to 0. So that's kind of conveniently right here. So this is going to be find horizontal tangent line. Let me label to keep stuff clearly what it is. Horizontal tangent line. So I'm just going to set this derivative equal to 0. And really, I've already factored my numerator. So what I'm going to do is I'm going to consider just the numerator part and kind of ignore the denominator till the end, because 0 divided by anything is going to be 0. So as long as I can find those x values where the numerator would be 0, All I have to check is that they do not make the denominator 0 as well. So I want to see x values that are not equal to 1, because a 1 would make my denominator 0, and then the slope would be undefined. I want 0 slope, not undefined slope. So I'm going to set that highlighted numerator equal to 0. So x times x minus 2 equals 0. That's pretty much in solution form already. That first factor is just going to be x equals 0. Second one, x minus 2 equals 0. If I add 2 to both sides, that tells me there's also a horizontal tangent line at 2. So I am looking for the points. So what I need to do is kind of forecast into part D. I know I need to graph this function. So I'm going to set up the table. Here's the function x squared over x minus 1. And I just need to plug in those x values at 0 and at 2. So again, I'm going to leave some space to give myself room to incorporate more values. I'll start with these two. So I'm just plugging into the function here, 0 squared over 0 minus 1. That's going to be 0 over negative 1, which is just 0. So I see it that at the origin, I'm going to have a point that is a horizontal tangent line. So I can actually sketch that horizontal tangent line in and write its equation. That's the equation y equals 0. The x-axis has the equation y equals 0. Let's calculate the y value when x is 2. So 2 squared over 2 minus 1 is going to be 4 over 1, which is just 4. So at 2, 4, we'll also have a horizontal tangent line. And that would have the equation y equals 4. Remember, you name horizontal lines based on where they cross the y-axis. So that completes up to part C. I found the points. In fact, I graphed the horizontal tangent lines and gave them their equations. That was for free. So what we need to do now is we need to just calculate a table of values for my function. So I'm just going to predict -2, -1, 1, and let's go up to 3. So it's a rational function. I see the numerator has a higher power than the denominator, so it's going to have a slant asymptote. But let's use the calculator to get our table of values just to speed through that task. Let's head over to Desmos. So I've written the function down. I just want to type it in, take a look at the table. So f of x equals x squared over x minus 1. So there's our function. And if I return to the home, we can get a good view. That's definitely a rational function with a slant asymptote or oblique asymptote. There's my table. Let's increase it to, in fact, I think -2 is fine because we got 3 points on the left. I do want to increase to 3 though. So we at least have those 2 points on the right. I definitely see that I've got an undefined value at 1. When I look at the graph at 1, I see that's where the vertical asymptote is. And then I have these other values, so -2, -1.3 repeating, -1, -0.5. It does go through the origin, which we saw. That's where our horizontal tangent line is. And I can see that's a relative max on the graph. And then it jumps up to 2, 4, and then 3, 4.5. Notice 2, 4 was also a horizontal tangent line. That's a relative minimum on that graph. So again, what we're seeing is there's a connection between where tangent lines have slope of 0. It's where the graph has either a high point or a low point, a max or a min. So I've recorded that table. Let's go back to our note screen to finalize that graph of the original. I'll just fill in the table right away. So -2 was -1.3 repeating. -1 was -0.5. 1 was undefined, which again we can interpret that's the vertical asymptote. And then at 3 we had the value of 4.5. So we're ready to graph this one. So -2, -1.3, -1, -0.5, 0, 0, then a vertical asymptote at 1. So that left hand of the side of the graph will look something like that. And then the right side jumps up to 2, 4. So that's that minimum value, and then 3, 4.5. So that gives us enough to make a rough sketch of the right-hand side as well. And we can just sketch in. We didn't do the actual equation for the oblique asymptote, but we can see that it's there. The last task that we need to do is to graph our tangent line. So that was from part B. It's 3/4 x plus 1/4. So what I want to do is just place it on our graph here. And I'm going to zoom in so we get a closer view, because I got some decimal values here. So again, it's the equation y equals 3/4 x plus 1/4. So I have to estimate the y-intercept is a 1/4. So that's roughly there, positive 1/4. And then it rises 3. So 1, 2, 3, and then it runs over 4. So 1, 2, 3, 4. And there's my tangent line. And I can see that here on my graph, it definitely is intersecting at that point, -1, -0.5. And that really confirms, hey, that looks like a decent tangent line. It's intersecting that left-hand branch of the rational function at 1 point exactly. So thank you for joining for this investigation of differentiating using the quotient rule and using that to find any horizontal tangent lines, as well as the slope of it, or slope and the equation of a tangent line at a given point. So I'll let you go work on differentiating your quotient functions. Thank you for joining. See you soon.